Okay, I'm Andres. I'm from Google. Thank you for attending this talk. Thanks very much. Thank you for coming to OCP. I'm in the platforms division at Google. We're responsible for making the machines for the data centers that all of our products use. Cloud, Gmail, you name it. Something wrong? Oh, the screen is like bleeping. Okay, I'll just keep on talking. Thank you. So within the organization, there are multiple things that we need to care about. Keyboard setup. Is that good?
Our systems are getting more complex.
Yeah, systems are getting incredibly complicated. That's the running joke. Yesterday we made a similar presentation, and again, figuring out the AV seemed more complicated than what I'm going to talk about now. One of the things that we care about is security, of course, but another is software. Think of this as the software take on system complexity and a message for the audience, right? So we're going to start with the code name of the project, which is TintenFisch. TintenFisch is German for fish that produces ink. Essentially the family of octopods, squid, etc. Now, it's not ink that matters. What matters is, for the purpose of this presentation, what matters is the metaphor. This thing have multiple limbs and multiple neurologic centers, right? They have multiple brains, and they also have multiple hearts. So we're going to come back to a metaphor in a moment. You should be very familiar with this. It's an overarching theme in our industry for the last 3 years or even more. It's, of course, a hot philosophical debate. Some people say Moore's law hasn't ended, other people say it has. But I think it's difficult to argue the fact that we used to scale up, according to Moore's law, pretty reliably, and now we're not doing that anymore, right? It's tapering out, or at least it's hitting a plateau, right? So one way to deal with this is, scale up is over. What do? You scale out. And that brings the rise of system complexity. When we're saying scale out, what we mean is you're not going to have all of your compute being serviced by a single CPU, right? So you scale out to specialized accelerators. There's a wide variety of this. We're not just talking about GPUs. We're not just talking about Google's favorite toy, TPUs, right? Even tasks such as system management, they're going off to BMCs. You have SmartNICs, they're doing packet tunneling, quality of service, even essentially network authorization. So you have a variety of specialized workload accelerators and offloads around your main CPU. So that's what gives rise to this metaphor of the TintenFish, right? Your server, which used to have one brain, now has multiple brains. It's really hard to say what a server is anymore. This is a mock-up, right? This isn't a Google platform. We do have complexity, but we don't have that much. But this is a mock-up to illustrate the scale of the problem that we're trying to deal with, right? At some point in the future, there are going to be systems this complicated, right? And most of the audience should be familiar with this, right? I mean, there are SmartNICs, of course, that have ARM CPU complexes on top of them. There are GPU trays being made by the GPU manufacturers with switches and roots of trust and BMCs and multiple GPUs. There are storage trays on the side with a wide variety of SSD fan-out. And of course, Google having inference trays that we do in-house as well for specialized. The point is, this is very, very complicated. There are lots of brains here. And just to re-emphasize something in our presentation from yesterday, OCP has done a phenomenal job at putting together hardware, right? You see OEM, you see DC-MHS, DC-SCM, all these things. This is hardware, right? It's amazing, it's fantastic. You have standardization, you have reusability. But how do you put it all together so that it works in the data center? That it works in the data center at the scale at which the industry and our customers are pushing us, which isn't 10 or 20 systems, it's hundreds of thousands or millions of systems. Certainly for workhorse systems, which are already getting very complicated, we're talking about the millions, but even for this mock-up system or very similar ones, it's definitely tens or hundreds of thousands of those. And this isn't just about plugging together the speeds and feeds and seeing the PCI packets and the Ethernet packets fly by. This is about all the journeys that we have in the data center that make us spend enormous amount of time and that we have to get absolutely right. Otherwise, we don't have availability. We don't have service. We don't make money. We don't have a business. Our customers cannot use things. So there's a list there. Not trying to just read the whole thing, but there's a general gist to this list. There's a machine life cycle. You have to bring it out from manufacturer, you have to turn it up, you have to take ownership of it, not just in the sense of installing your software, but also installing your keys. Over time, these things get rotated, software gets upgraded, keys get renewed. Eventually, you get rid of the machine. In the meantime, you have to maintain it. You have to know if a chip is melting down, if a fan stopped working, if you're having voltage glitches, if you're getting PCI errors, if you're getting MCEs out of the CPUs. All of these things you need to find out as well because you need to maintain the system over time. All of this is business continuity, it's business value, right? So we need to deal with this complexity when systems are this much complicated, right? When they have so many different brains. So our approach has 4 organizing principles. I'm going to talk about it. Then we're going to emphasize double click on each of those and kind of throw a challenge, for lack of a better word, to the community to join us in this journey, right? The first organizing principle is we try to take a look at a first principle look at the problem and say, okay, how do we actually organize this? And that's by modeling, right? An entity relationship-based model, which you can see here, doesn't really matter what it is, it's not meant for human consumption. What it is meant for is for automation to walk the model and understand the dependencies between the entities. It's an entity relationship model, right? So if networking to get to a given part depends on some other part, you cannot shut them off out of order because then you black hole something. So that's one example, right? If you have shared power domains, you need to make sure that all the operating systems have shut down and flushed their buffers before you pull the plug on the shared power domain. Otherwise, you run into problems, right? So those are the kinds of things that the model provides for automation to walk in the correct order, right? This is how we're going to hit the reset buttons. This is how we're going to upgrade the firmware. It's important to have a single source of truth for topology, and that's what this is. So this is one of the things that we would like to hear back, see if it piques your interest, and if you want to collaborate with Google on where this is going. This is based on UNM, Unified Network Modeling, which is something that Google published in NSDI. And that we have, it's out in the open domain. This is taking that to the next step. The other part is breaking the problem, divide and conquer, a classical systems methodology. The unit of division is something that we call an arena. An arena is a self-contained unit of hardware management. So if you look back at this drawing, there's a lot of composition that is potentially going on, right? You can imagine a system with 1 SmartNIC, a system with 8 SmartNIC, a system with 1 GPU tray, a system with 2 GPU trays, a system with 1 tray and 1 storage, or a system with 2 storage trays. These things are happening. Different customers have different needs. That's the flip side of acceleration. Acceleration is domain specific. So instead of having a common workhorse platform for all your users, now we're going into an age of specialization. Specialization means composition. Composition means arenas. Arenas are the composable unit of hardware management. And in order to compose, arenas have to be on the network so we can talk to them when the service is walking the model and deciding to talk to something. And they have to provide out-of-band management so that the arenas are actually in charge of the management, right? So we're not good friends of in-band management for these reasons. In-band management means we need to find ways to talk to each individual vendor, interrupt the user into whatever they're doing. So this is sort of the put it together slide. That little cloud over there on the side is production services. That's not really something that we guess it's going to be much of interest to you because it's about installing 10,000 machines in a cluster. That's what that production service is about. So it's not a common problem that people have. But our production systems walk the model and talk to the individual arenas. The individual arenas are the problems that all of us have. They are firmware and software from devices that are off the shelf. Some of the arenas are off the shelf. And that's where we want to work together with you and with the multiple tracks in OCP that make these arenas, because these arenas are hardware, and bring it to the next level. Talk about the hardware management, talk about the out-of-band, talk about the software. One last thought for you. Once you've broken down the problem into a problem of arenas, this aggregation becomes incremental. When you have a shared pool of resources, it's just another arena in the distributed system. There is a very tricky additional problem, which is your failures used to be localized. this SSD failed and it happens to be in the same tray as this user, so it's obvious who's getting affected. But once you go into disaggregation, it's not so obvious anymore, right? When you have an SSD failure that is shared across many different tasks on many different quote-unquote machines, that's a not so obvious problem. So I would like you to start thinking about how we're going to be doing that mapping. But the main point here is we believe that our approach, and we're seeing this slowly come to fruition in practice, makes disaggregation incremental as opposed to subversive or disruptive. Call to action, just reinforcing the last couple of things that we said. Please join us, talk to us, not just me. Siamak, there are members of our team over there, Richard, Ed, others. Let's talk about the arenas as the hardware modules that OCP is churning out. And let's talk about the out-of-band hardware management software that we need to put together as part of that. And if you want to talk to us about modeling, we'll be very happy to do that. I think that's the end of the presentation. I don't know if we have a minute or two for questions or whatever. Thank you. Thanks.